All right, lesson 19.2, graphs of rational functions. So you'll be able to sketch and graph a rational function. Now recall that a rational number is any number that can be written as a fraction. Okay, so all whole numbers can be written as fractions by putting them over 1, right? 0.3 is a rational number because I can write it as the fraction 1/3. Square root of 49 is rational. E, pi, square root of 12, all of those are irrational. All right, so a rational function now is a function defined with a polynomial in both the numerator and the denominator. G of x cannot equal 0. As we discussed last section, we know that having 0 in the denominator makes the function undefined. Okay, so recall x-intercepts. X-intercepts, we set y equal to 0 and solve for x. Right, algebraically, that's what we do. If we think about a rational function, if I set y equal to 0, I'm only looking for where my numerator is equal to 0. Okay, so I would only have to set the top equal to 0 because 0 divided by anything would give me 0. So our y-intercepts, similarly, we set x equal to 0, solve for y. So you will need both the top and bottom for that one. Our domain restrictions, we've looked at domain all year long. Our domain restrictions come from the values of x that would make the denominator equal to 0. So we set the denominator equal to 0 and solve. Okay, now we did a lot of work with limits. Recall from last lesson, if the limit as x approaches a number, if direct substitution gives us number over 0, then that graphically is a vertical asymptote at whatever the value we were approaching. If we take the limit as x approaches c and we get 0 over 0, remember that could be some other type of discontinuity. So what we looked at is it was a hole at the point c comma whatever the value of the limit was after we did some simplifying. Okay, so the general outline for graphing rational functions. We're going to, first and foremost, you factor, okay? And I'm actually going to, before simplify, part B, determine domain restrictions. Okay, the factored form enables us to do it more easily. Domain restrictions. But before you simplify, which I'll put as part C, you want to use the factored denominator, and that gives you the x values that don't exist right away. Okay, so we have to find the x-intercept. We find the x-intercepts or the zeros. We find the y-intercepts. We're going to plot those points. Vertical asymptotes, they're the zeros of the denominator. Okay, they'll come directly from us determining the domain restrictions. Non-vertical asymptotes, horizontal asymptote, recall from last lesson, that's the limit as x approaches, not c. The limit as x approaches infinity. Okay, if that evaluates to a number, then that y value is where our horizontal asymptote is. Okay, and we talked a lot about the difference between that. A sign analysis test. So these are just general sketches, and you're going to see after the first few what I mean by how important the asymptotes are to the graph of the function. But your sign analysis test, you'll use zeros and domain restrictions. Okay, and you'll know what I mean when we do our first example. Okay, so let's graph. So first I'm going to find my x-intercept. My x-intercept, I set the numerator equal to 0 and solve. So when my numerator equals 0, my x-intercept will be at the origin. Find a y-intercept. I set all my x's to 0 and solve. Okay, so your y-intercept is also at the origin. Next, domain restrict. So I should actually start here. My domain, it's already in factored form, so I know that x can't equal 1. Okay, so then what that tells me, since my domain restriction is 1, if we were to attempt to find the limit as x approaches 1 of our function, it would give me number over 0. So I know that this domain restriction will be a vertical asymptote. Okay, next, horizontal asymptote. So I'm going to do the limit as x approaches infinity of my function. Now that's where we have to go back to our top heavy, bottom heavy equal. So highest exponent in the numerator matches the highest exponent of the denominator. So my limit here is equal to 1. Therefore, I have a horizontal asymptote at y is equal to 1. Okay, so let's put these things in. X and y intercept there. Vertical asymptote at x is equal to 1. Horizontal asymptote at y is equal to 1. Okay, so now our sign analysis. So I'm just going to do a quick number line. So my 0 of the function occurred when x is equal to 0. I had a domain restriction at x is equal to 1. So if you look on the x-axis, what those values do is they break the graph into different regions. So I'm going to have the same behavior for all values less than 0. I'll have the same behavior for all values between 0 and 1. And then I'll have the same behavior for all values bigger than 1, for x values bigger than 1. Now the asymptotes are going to make sense when we actually start drawing it. So these are sign analysis. These are test values. If I take a negative number and plug it back into my original, all right, the original is x over x minus 1, I'd have a negative numerator over a negative denominator. So that would give me a positive output. If I test x is equal to a half, that'll give me a positive numerator all over a negative denominator, therefore making all my outputs negative. If x is equal to 2, I plug that in my original, positive numerator, positive denominator. So this is positive. Okay, what exactly do these things mean? If I'm plugging x values in, then my outputs are my y's. So what this tells me, if my sign analysis is positive, that means my graph is going to be above the x-axis. All my y values have to be in the positive region. Likewise, if my sign analysis gives me a negative region, that means the graph of my function is going to be below the x-axis, where all my y values are negative values. Okay, now it's a little bit tricky for this one, just because the x-intercept and the vertical asymptote are so close. So look at what's happening. For all values of x smaller than 0, my graph has to be above the x-axis. Whenever you have an asymptote, you always have to hug the behavior of the asymptote. So I'm above the x-axis. I have my x-intercept. That makes sense. It also happens to be our y-intercept. Now between 0 and 1, my graph has to be below the x-axis. So once I cross over at the origin, notice now I'm going to hug the vertical asymptote on the way down. So now, bigger than 1, my graph has to be above the x-axis, and I have to hug the behavior of the asymptotes. So this portion has to strictly be in quadrant 1. So there's my graph. Let's do another one. 1 over x plus 1 quantity squared. Okay, domain, denominator cannot equal 0, so x cannot equal negative 1. Okay, my x-intercept, if I set my numerator equal to 0, that's not a true statement, so there's no x-intercepts. For my y-intercept, I solve for y when x is equal to 0. So my y-intercept is going to be positive 1. Okay, so 0, 1 is going to be a point that I plot. My domain restrictions, if I look at the limit as x approaches negative 1 of my function, I don't know why I wrote infinity, of 1 over x plus 1 squared. That's going to give me 1 over 0, so I know that that domain restriction is going to be a vertical asymptote at negative 1. Next, horizontal asymptotes. If I take the limit as x approaches infinity of my original, when we approach infinity, we can compare top heavy, bottom heavy equal. The only x is in the denominator, therefore it's a bottom heavy, and the limit of the function is 0. So we would have a horizontal asymptote at y is equal to 0. Okay, so let me get those things on the graph. Y-intercept at 0, 1. Vertical asymptote at -1. Horizontal asymptote on the x-axis. Now, when we go to graph this, there's no x-intercept. So my graph can never cross over the x-axis. So that's going to be a very important piece of information. Okay, next, sign analysis. The only value that I have on the x-axis is my vertical asymptote at -1. Okay, so if I choose -2, I go back to my original. My numerator is always +1. Now look in your denominator. In your denominator, you're squaring any number, so that would remain positive. So this interval is positive. If I choose 0, when x is equal to 0, we actually already did this because that's where our y-intercept is. Positive numerator, positive denominator. So what does this mean for our graph? Our graph is strictly going to be above the x-axis because both of those outputs were positive. Okay, so here I am. I'm to the left of my vertical asymptote at -1. My graph has to strictly be above the x-axis, and I have to hug the asymptotes. So there's my graph to the left of -1. Now to the right of -1, above the x-axis, hug the asymptotes, and we have this added benefit of having the y-intercept. So it gives us direction. It tells us we're plotting it properly. All right, hopefully this one is a little bit familiar looking. That's 1 over x squared. That's your inverse squared parent function. And then what did we do? We just did a vertical translation. No, I was right. Horizontal translation of 1 unit to the left. All right, let me see if I can set up one more. There will be a second video just with more examples. Okay, first start with the domain. My denominator can never equal 0. X squared can never equal -1. There's no restrictions. So my domain is all real numbers. Okay, so start with our x-intercept, set the numerator equal to 0, not a true statement, so there's no x-intercepts. My y-intercept, set x equal to 0, so I'll have a y-intercept at 4, the 0.04. Okay, since your domain was all reals, there can't be any vertical asymptotes on the graph of the function. There's nothing to investigate the limit. Possible horizontal asymptotes, I'm going to take the limit as x approaches infinity. Okay, the only x is in the denominator. So that limit is 0, therefore I have a horizontal asymptote at y is equal to 0. Okay, y-intercept at 0, 4, no vertical asymptotes, but I have a horizontal asymptote on the x-axis again. Okay, sign analysis. Now notice here, I don't know why it keeps doing that. There's nothing on my chart. There's nothing I can put on my sign analysis. I have no x-intercepts. I have no vertical asymptotes. There's nothing that crosses the x-axis. So no matter what value of x we pick, if I pick x to be -1, plug it into my original, I'm always going to have a positive numerator and a positive denominator. X is equal to any number. You're squaring that number and adding 1 to it, so it's going to remain positive. So graphically, we are strictly above the x-axis. So now let's put it together. I got to hug my asymptote at the end here. I have to get up to 0, 4, and then I have to come back down. And I'm just going to trace over it. The important thing for you to see is if your domain is all real numbers, that means your function is continuous. So I should be able to graph my function without ever having to lift my pencil. So from left to right, I'm certainly able to do that. I have to keep the behavior and go through my y-intercept. We'll finish this one, go to the next video for more examples.